All right, we left off last time. A little bit of winter came back, man. A little chillier out there. It's going to be chilly a couple days, next couple days from what I hear. Got a nice warm weekend. This is a little thing that's actually not in the book, I don't think, but it's a little how should I say? It's a tool that will it makes certain calculations a lot easier. My wife and I use it in our own finances. We use it quite a bit, actually. It's approximate, but it's pretty good. It's called the rule of 70, and I'm going to add 69 or 72. Sometimes you see the rule of 72. 69 is a secret. Okay, I'll tell you why in a minute. It gives you the time required to double your money at a given interest rate. So suppose you know the interest rate you're going to have, or you make an assumption what you're going to have, return in the stock market or whatever. You divide that into 70 or 72, whichever one it goes evenly. And that gives you the number of years it takes to double your money. To double your money at that interest rate. The other way around works. If you want to double your money in, say, 8 years, you divide that into either 70 or 72, whichever one it goes evenly, 72 in that case. And that gives you what interest rate you're going to need to double your money in, say, 8 years. It'll be 9, right? So one more thing. This is the only time that we're going to use percent interest rates as whole numbers, right? In the book always uses it as a decimal, and I want you to keep doing that for anything else we do regarding compound interest. Only for this thing, which is not in the book, by the way. Like I said, I don't think it is. This assumes compounding, and it's pretty accurate. Here's how this works. Use the rule of 70. Now, when we say rule of 70, we mean 70, 72, or I'm going to give you one instance where 69 actually works better. Okay? 69 is the real number, by the way. 69 is the real number. The problem is not many things divide evenly into 69. Only 3 and 23. So if you're ever interested in 3 years or 23 years or 3% or 23%, 69 is the number you should use. It is actually the closest number. So we use 70 if we can. If not, we use 72. Okay. So approximately how long will it take to double your money at 6% annual interest? So it's asking for how long. Your answer is going to be in years. Right? So we have 6% goes into 70, not even. Goes into 72, right? So 72 divided by 6 is what? 12 years. It's that simple. You just divide it into 70 or 72, whichever one it goes evenly. And that, boom, in 12 years, you will double your money at 6% interest, compounded, right? Now, we saw earlier that compounding daily, monthly, yearly makes only a little bit of difference, okay? Only a little bit of difference. 10% annual interest, you pick the number into which this divides evenly. So 70 in this case. You use 70 in this case because 10 goes into 70 evenly. That gives you 7 years. So if you go from 6 to 10%, the time it takes to double your money decreases. You'd expect that, right? Works the other way around. How long will, or approximately what compound interest rate is necessary to double your money in 7 years? It's the opposite of this, pretty much. So we take 70, because 7 divides it evenly. 7 goes into 70, 10%. And like I said, this is one time where we use percents as whole numbers, right? Not as decimals, right? In 3 years, well, 3 years, this is the special case where you use 69. Whenever it's 3 or 23, because those are the only two things that go into 69 evenly. So if it's 3 or 23, you divide into 69, and that is 23%. So if you want to double your money in 3 years, you need 23% interest. That's it. That's it. That's the rule of 70, 72. Here's some homework. It's just what we just did, right? This is a quick little tool. It's not exact. Very close, though. It's very close. Stuff that will be on the test. All right. We are coming in on the end of chapter 4. Today is Wednesday. We will finish chapter 4 on Friday. We're going to finish chapter 4 on Friday. So we're going to call this test for next Wednesday. That will be the, I'll give you enough time. That is the 14th. So chapter 4 test. Just do this right here. I'm going to back up one. All right, next Wednesday. April 14th. All right, so make your plans accordingly. A week from today, plenty of time to study. If you wait till next week, you're going to get toasted. Don't wait till next week to start studying. I'm saying that for your own benefit because honestly, this stuff is it's new to most people. And it doesn't cram well because it's conceptual in nature. Here's stuff that's going to be on the test. Right? Some of these can combine pretty easily. Probably won't be a separate question for everything. Right? But we went over one-to-one functions, composite functions, which is when you plug a function into a function. One-to-one functions, horizontal line test. A one-to-one function carries different x values to different y values. Remember that? Only one-to-one functions have inverses. So finding and graphing the inverse of a one-to-one function, right? The graph of an inverse of a function, of a one-to-one function, is the graph of the function reflected about the line y equals x. Finding the range and domain of functions. We did several of those. Exponential functions, properties, graphs, range, domain, etc. Logarithmic functions, properties, graphs, range, domain, etc. Way too much for you to cram in a night. Way too much. If you haven't been doing homework other than the homework I gave in class or in the slides, I would get, as my daughter would say, I'd get a crack-a-lackin'. Look on the course guide for every section. There's some recommended problems. You go in there, you do the problem till you're fluent at it. You do that type of problem till you're fluent at it, right? If you're missing your layups, you don't practice your three-pointers. You practice layups. You practice what you're weak at. Compound interest, we just went through. Exponential growth and decay, we're about to do. Label key points and features on all graphs. All right. Also, up till now, you know that I've pretty much always asked you to graph something without the calculator. There'll be a calculator section and a non-calculator section of the exam. I've pretty much asked you to always graph something without the calculator because I want you to understand the components of the graph. But equally difficult has been to graph something with a calculator. And so you're being asked to graph something with a graphing calculator. And this is an exercise, a little bit of an exercise in technology, but you also need to understand the function in many cases in order to properly interpret what's on the screen. Every aspect of our society just about has screen input or output to interpret. Very, very important. Very important. So anyway, that you can expect to see. We're only going to do these items 7 and 8 as we did in class. We skipped a lot of these sections. Okay? Exponential growth and decay. I got good news and bad news. The bad news is, you want the bad news first or good news? The bad news is, as usual, as has been the case in every chapter, where's the hardest section? At the end of the chapter, the last one of the chapter. Because then you're applying things to that chapter, right? And so the last two sections, compound interest, I'll be honest with you, it is something students normally do well on the exam. They normally do pretty well. I mentioned before, on an exam, I expect you to put down the relevant work. So in other words, if you give $808.08, put down the formula that you entered into your calculator, right? You don't have to do that math by hand, but I want to see that on your paper as your backup work for that answer. That has two advantages. One, it shows me that you knew where that number came from, and it didn't come from somewhere else. Number two, it allows me to give partial credit, because you can miss, especially in one of these down here, you can miss just one of these numbers and your answer be off by a lot. A lot. You miss that negative sign, your answer is off by a lot. But that's a small mistake. So that is a smaller deduction, right? Whereas somebody can sometimes miss all the numbers and get something close, right? You're going to want to see the work, whatever it is you enter into your calculator to support your answer, right? Another thing that happens is that someone has the work entirely correct. This is entirely correct, but their answer is wrong. What does that mean? Typo. You entered into the calculator wrong, right? That is a small deduction in my mind, right? That's a small deduction. So get the supporting work. But this section is very applied, very real life. Exponential growth and decay, likewise, this is very applied, very real life. This stuff is all around us. It's all around us. I've mentioned before, almost every issue, you pick up a newspaper. Remember those? They were big. They had these thin sheets of paper, and people would read them to find out what's going on. Some people, yeah. You pick up a newspaper. You go on USA Today website. Other than complaining about who's president and what Congress is doing, or supporting who's president, what Congress is doing, you look at the bottom of those issues, and you have an exponential function in the majority of cases. Spending, national spending, exponential function. Exponential, it's a compound interest, right? National debt, compound interest. It's an exponential function. Overcrowding in here or there or whatever, exponential functions we're going to see in this particular graph. Most environmental issues, exponential function somewhere there, right? So, okay. A population, A. A is the amount of the population at any given time. It follows the law of exponential growth or decay, and I'll tell you when it's decay. If its amount at any time t is given by, and this is a very important Relationship. Don't just memorize it. Remember, know how to use it. If you don't practice these and a bunch of them, you won't get it right on the exam. I can promise. Just doesn't work. Also, as we're going to see, this is one of those topics where you're given a scenario and there's multiple parts to the problems usually. There's a lot you can do once you have the relationship, but you got to get the relationship. All right. Now, in this relationship, the amount of a population at time t is the independent variable. It's the x, if you will. A is the dependent variable. It's the population or however much you have of something. We say population whether the item under consideration is living or not. Population could be, we're going to use A even for stuff like amounts of uranium left or something like that. We have an example in the notes. All right. K is the exponential growth constant. This K. That is different for every problem. And you have to know how to find it by hand. By hand. And I'm going to show you a couple of times. If K is positive, it turns out this will slope up like an exponential function. If K is negative, it will decay. So it's called exponential growth if the growth constant is positive. It's called exponential decay if the growth constant is negative. Notes, many populations, I've mentioned this before, many populations initially grow exponentially for some period of time while there are no limits on resources. Okay? When there starts to become limits on resources, the growth rate slows. And as it turns out, it even flattens. And that is, if we ever get to those sections, that is, excuse me, called a logistic model. Logistic. That takes into account the flattening off. Radioactive substances decay exponentially. All of them do. Continuously compounded interest grows exponentially. Right? Look at this. This was our compound interest formula right here, right? Look here. The growth constant is the interest rate. In the continuously compound interest formula, your growth constant is your interest rate. And so if you're told that what's happening right? Sandhill cranes, that's what's happening right now. This time of the year, sandhill cranes are coming through Nebraska, further west, right? You want to know about sandhill cranes? Talk to Dr. Kite. He knows everything there is to know about sandhill cranes. It's beautiful to go see them. Just tens of thousands of these birds, and they have like I think it's 11,000. I think from Siberia to somewhere down in South America. It's amazing how far they go, and they land in Nebraska every year. It's kind of cool. What's my point? If you're told that the sandhill cranes are increasing by 1.5% per year, 1.5 is your growth constant as a decimal. So it's 0.015. It's your growth constant. So you like problems where they give you how much it's growing or, for that matter, decreasing every year. Here we go. The number of feral hogs on a ranch are growing exponentially. There were 200 in the year 2005. There were 12,000 in the year 2016. And if you think I'm kidding, you're not from Texas. Texas and Oklahoma, they have and some other parts now, they have a problem with feral hogs. They grow a lot, and they grow fast, and they have they're aggressive. They have no natural predators except crazy people like me who go shoot them over Christmas break. Went hog hunting over New Year's, actually. Down there in Texas, lots of hogs, right? So you're told some things. What I recommend, here's your formula. What I recommend is the same thing as for compound interest, or for that matter, any other word problem. Try to identify in the problem the components of your formula. They all may not be there, by the way. Okay. So I tell you what, let's do a little graph, shall we? Let's do a graph. This is time in years. Yeah. And this right here is the number of hogs. Right? That's one of my many skills, making gross little boy sounds. There were 200 in the year 2005. Now, you remember that year 0 is not Genesis 1:1, year 0. In the beginning, God, right? That's the real year 0. But for purposes of these problems, year 0 is going to be your first, when you begin observation, the beginning of your period of observation. And so when we say year 0, we mean we're talking years, but years since. Year 0 is 2005. Right? And this is not just years, this is going to be years since 2005. So let's go back up here. 200, that's how many you're starting with in 2005. That is A0, your starting amount. You remember in compound interest, your present amount was the P, it went there. That was how much you have now. So A0 is A evaluated at time equals 0. All right, so this 200 is A0. The year 2005, this is T equals 0. There's 12,000 in 2016. So 2016 is A evaluated at year 11. And 12,000, I'm sorry. Ooh, sorry. Typo. 12,000 is A evaluated year 11. 2016 is T equals 11. All right. So you label stuff up there. Now, what do we know? Let's put it in a graph. A graph is not absolutely necessary. The problem doesn't ask for a graph. It could, by the way, it could. But this problem hasn't asked for a graph yet. It's for your pedagogical enhancement, for your learning, okay? So in the year 0, we have 200 hogs. In year 11, there's 12,000. Oh my gosh, 12,000 hogs, right? So what does that say? That says your graph is growing like this. Yeah. All right. Find a growth model for the number of feral hogs at any time T. So our model is this. A is, that's a future amount, A0 e to the k t. Note, must find two things. Number one we have to find is A0. Because in our formula, those are all letters, but you have to understand what they are. E is the number 2.7 and change, right? So there's no finding E. T is your independent variable. We need to find A0 and K. There's two things that we need to find in order to have the model. So A0 is there. So we're going to plug that in. That's 200 e to the kt. See what we did? We plugged it in where it belongs. Now, here's what I need you to understand. We were given, over here when we did our graph, we were given 2 points on the graph. We're giving a starting point, and we're given its value at year 11. It turns out that if those 2 points are not at the same level, they don't have the same y value, or they're not above each other, that they don't have the same x value, if those two things are true, then there is exactly one exponential function that goes through these 2 points. There's only one. So we have sort of harvested the information of this first point. In other words, we've used it. How did we use it? We used it with 200. This is saying when time is 0, the population is 200. We've used the information in that point. Now we're going to use the information in this point. How do we use the information in that point? Well, what are the coordinates of that point? The coordinates of that point are 11. That's the independent value, and then 12,000. So that says what? Go over to our model. Oh, by the way, now we have found A0. We need to find K. All right? So over here in my margin, I'm going to say find K. That's what we're doing now. That point up here, that point there, says in our model, when we plug in 11 for t, this says when we plug in 11 for t, then it equals 12,000. That is what that point up there says, is that when the independent variable t is 11, the dependent variable a, and this should be a, this is a, should be 12,000. All right. What does that do? Well, all these are numbers. E is a number. The only thing left is K. So now we're going to solve for K. You need to know how to do these next steps. The next steps are how we solve for K. First thing is you divide by the 200. So you're going to have 12,000 divided by 200 equals e to the 11k. All right. We've got some canceling that goes on here. We can cancel 2 zeros in the top, 2 zeros in the bottom. And I'm actually going to switch sides. That is 120 divided by 2 is 60. E to the 11k is 60. I like putting what I'm solving for on the left. That's why I'm doing that. Just a habit. You don't have to do it. Question. What method did we use to get what we're solving for out of an exponent? If our unknown is in an exponent, what did we do to get it out of the exponent? We took the log of both sides to whatever base that is. We took the log of both sides. So on both sides, our base here is E. Our base is E. We're going to take log base E of both sides. So that looks like this. Log base E is natural log of the left, natural log of the right. Why did I pick natural log? Because natural log is a logarithm base E. That's the base. If this was 2 to a power, I would have taken log base 2. Log base 2. All right. So now, natural log and E, these are inverse functions. Natural log and e to the x are inverse functions. One undoes what the first one did. So the left-hand side is just 11k. That is why you took logs on both sides. It gets that k out of the exponent. Right-hand side is natural log 60. So k is natural log 60 divided by 11. That's just an oddball number, but it's a number. Natural log 60. What is natural log 60? It's the power you have to raise its base to, E, in order to equal 60. Now, you're not expected to know that. You can leave your answer just like that if it's by hand. You can leave it just like that. What does that mean? That means we have the model. So, ergo, the growth model is A is 200 E to the natural log 60 divided by 11 times T. That is the answer for part A. I'm going to go back through that, but I hope by now I've convinced you that if you haven't done a few of these, just flip the page on the test because you're not going to get it. You have to do a few of these. Right? These are the kind of thing teachers have to review. Any questions? I'm going to go back through it. Number one, read the problem carefully. I've said before, if you have a reading comprehension issue, you read one of these and it just makes you're glazing over, and you might have a reading comprehension issue. I would speak to somebody in the Edge Center. And there's no shame in doing that. I did it when I was in graduate school. I took a speed reading class. I think I told you about it one time. I took a reading class. I was in graduate school. I was 25 years old. Had 2 master's degrees. Right? I was reading like I had a good vocabulary, but I was reading very, very slow and low, and not the comprehension I should have. Right? So you go up in your problem and you label the components of the function of our relationship. You go label stuff. All you're doing there is you're opening up your spice rack and you're saying, hey, I got mustard seed there, I got oregano here, I got garlic powder there. You're identifying what you have to cook with. And your formula is your recipe. That's your recipe right there. So I find the components. I label 2005 as t equals 0. 2016 as t equal 11. $200 is how many hogs I have at 0, at time 0. That's A0. 12,000 is how many hogs I have at the year 11. And those correspond to 2 points on a graph. Again, you don't have to do a graph. I think in a lot of cases it will help. So your initial amount at 0, you have 200. Well, that means A0 is 200. Okay. The next part we do is we harvest the information in this other point, 11, 12,000. That says when in my formula, when t is 11, my population is 12,000. So I plug that in and I solve for k. If you haven't been looking at logarithms, if you haven't been looking at the exponential functions, honestly, if you haven't been turning in homework that you've done, right? There's answers to homework everywhere. There's people that will do homework for you. Obviously, that doesn't help you very much. But you plug those in, do a little simplifying. I like to put what I'm looking for on the left. So I have an e to the 11k right here. Take natural log of both sides. Why natural log? Because I have log base e here. That's the inverse function. So the natural log and e undo each other. Gives you just 11k on the left. Natural log 60 on the right. You divide by 11, you're golden. You have your k. And so this is your answer. This is what I'm going to be looking for on an exam. Now, you're going to be using this now. We're going to be using this now. So the calculator is going to enter in here. In fact, it's going to enter in right now. Any questions before I go on? This is the guts of the problem. If you get this, you can get the rest. Usually. We want to put this into our calculator. And we're going to do it in such a way that we do not round anything except our final answer. Do not round any value except your final answer. Because when you round stuff and you raise it to powers and everything, that rounding error just goes haywire. So I'm going to show you how to do that. This K, for example, this is the percentage growth rate per year. Percentage growth rate per year. All right? Let's see. What we're going to do, we're going to get the calculator out. And the first thing I'm going to do is I'm going to compute that K. I'm going to compute that K, and I'm going to store it in memory on my calculator. You don't round it. Now, you can put it on your paper as rounded, but you don't round it in your computation. So our K was what? Natural log 60 divided by 11. Now, I want to store that in memory. Your calculator has a lot of different memories on it. We're going to use, and it's over here on the right, STO, STO. Okay? I'm going to take the value of that expression, STO, and when you hit STO, it just puts that little arrow there. That's it. Now I'm going to give it a memory in which to store it. Since this equals K, and me being the creative genius I am, I'm going to use register K. Register K is above the left parenthesis right here. You see the little green K? There's a bunch of green letters up there. You can store it in any one of those. You want to store it in W? Have at it. So I'm going to store it in K. How do I do that? Don't press left arrow or left parenthesis. That will give you a left parenthesis. You hit the green button and the left parenthesis, and that gives you a K. So this means I'm going to store that value in K, hit enter. All right, hit enter. And I am going to put that buzzer on my screen. Right. Sorry, here we're going to make it smaller, and we're going to do a cut here. Okay. All right. That's our number. So this here equals around 0.3722. Or 37.22%. Them hogs are growing fast. 37% per year. And by the way, that's about right. That's about right. All right. Now, what do? We want to put this function into our calculator. Go back to your calculator. Go to your, up here to your function menu, and we're going to put this in 200, then E. Never put 2.72 for E. Use your exponential function. That is second e to the x. Now here is the cool part. You could type in natural log 16 divided by 11 in there, or you can just put K. Alpha K. It's stored in there now. You can use it the rest of the problem, right? And then my independent variable is X. Is X. All right? We've done this before. Zoom. You go to graph it. Oh, you actually got a piece of the graph right there. I wasn't expecting any of the graph. Right? That's not a very good graph, is it? Right? That's not a very good graph. We want to get part of this graph. We're going to have to get our Y value up past 12,000, probably to like 50,000. Right? So we use our window, and we're going to go, oh, minus 10 to maybe 50. I don't know. Well, not even that far. Let's do 30. Then X scale, let's do 10. Y minimum, oh dear, let's do minus 5,000. Y max, 30,000. Y scale, 5,000. You don't have to use the same values I did. I just want to get enough of the graph on the screen. I may not have gotten it right, or at least I may not have gotten it the way I like it. Hit trace. Yeah, them hogs are growing fast, right? Okay. All right, now we're not going to use this. We don't need this for the first part of the problem here. I just want to get the function into the calculator. Now, part B, let me how many feral hogs will there be in the year 2020? All right. Let's get this out here. Erase that. We're interested in if T equals 0 is 2005 2020 is t equals 15. Turns out the hogs, they don't get COVID, right? Turns out. All right, so they grew just fine in 2020. And so our answer is going to be A of 15 is going to be 200. E, natural log 60 divided by 11 times 15. Now you can crunch that out on your calculator if you want, right? Or you can go to your calculator over here. Calculator screen. When you have the graph, just punch in 15. 1, 5. Uh-oh. I need to get some more. A Y. Let's see. I only went up to 30,000. Let's go to 75,000. My graph's not big enough. Okay. Then I do 15. 53,184. The only problem here is this is an old screen. I changed the problem here. I changed the problem. I didn't have the hogs growing fast enough, and I forgot to change the slide, this part here. So on your calculator, on the screen that's on your right, put in this new number right here. Write in this number. So there's going to be 53,184 hogs. We are out of time. Oh, shucks. Right. We'll finish this one next time. And we have one more problem to do after this. I think one more. And that will be it for the test. Right? That'll be at the end of chapter 4. You might want to plan on visiting either my office hours, the tutor. We have the tutoring hours right there. There's at least one math tutor there. And of course, Spark on Monday night. See ya.